Okay, so topic of the day is using integrating factors to solve dy dx plus py equals q, where p and q are functions of x. So we really are, it has to be in this form to use this method. So as an example, I have dy dx plus 3y over x equals sine x over x cubed. So q would be sine x over x cubed, p would be 3 over x, and then I've got a dy dx and a y. They're the only y's in this equation. So just bear that in mind as well. For this one here, you can reverse the product rule by multiplying 3 by x cubed. So we can do x cubed dy dx plus, 3x squared y is equal to sine x. And then if you do differentiation with respect to x of x cubed y, then that takes you to there, and then you can integrate both sides to solve it. We're only considering exact equations, so we're only considering ones with this y, dy dx. If you notice what's happening, that is a function of x there, and this here is a function of x differentiated. And once you're in that form, then you've got your reversing the product rule technique you can use. The integrating factor for this one is x cubed, and it's what you times the equation through by to get it into a form where you can reverse the product rule and integrate. So integrating factor is x cubed, so it's what you multiply through by. So we've got to mimic that, but we need a more general case because it's not always that obvious. So I showed you this one earlier, but for instance, if you've got dy dx minus 4y equals e to the x, this is solvable. Something you can multiply through by to solve this, if we didn't find it earlier. But there's a technique we can use to make that easier. So considering a general case, so I've got dy dx plus py equals q. And I'm going to let my integrating factor be f of x. So first thing I'm going to do is multiply through by the integrating factor. So you get f of x dy dx plus f of x py. Remember, p is a function of x equals f of x times q, where q is a function of x. We need the left-hand side to be in this form here. So we need it to be f of x dy dx plus f dash x times y for it to be a reversing the product rule. And so considering the left-hand side, it's called being exact. If you see that in a book, that's what that is. So we need f of x dy dx plus f of x differentiated times y to equal this lot here. So it's f of x dy dx plus f of x times p times y. So this bit's fine. It's this bit here where we've got issues. So this implies that f dash x needs to equal f of x times p. Dividing by f of x takes us to there. And when you have a fraction where the top of the fraction is the bottom bit differentiated, if you integrate that, you're going to get ln of f of x. So what we're going to do is integrate both sides with respect to x. So I'm doing the same thing to both sides of the equation. I'm going to integrate the right hand side but leave the left hand side as it is. So that gives me ln of f of x. We don't particularly need to worry about the plus c at this stage because there's another plus c coming out of here, so we can not worry about that. And then if I do e to the power of both sides, f of x is equal to e to the integral of p dx. And so this here is your integrating factor. And so that's a general case which you can apply to any differential equation which is in this form here. You just need to get something you can integrate on the right hand side. Obviously in exam questions it's fine, but yeah, in real life things aren't always quite that straightforward. So integrating factor is e to the integral of p dx. And I'll go over a couple of examples of using that.